Hello everyone, I'm Wei-Kai Elaine. I'm going to talk about our work on improved constructions of perfectly oblivious RAM. This is a joint work with Hubert Chang, Elaine Shi, and Kartik Nayak. In the problem of oblivious RAM, we consider the scenario of outsourcing storage. We have a client that's a mobile device, has limited storage, so it outsources a huge data to the cloud server. The data is accessed piece by piece between the client and the server, but the cloud storage can be compromised or corrupted by an adversary, so the client encrypts all the data pieces and keeps the secret key on the client side. But this is not enough to protect the data because the adversary sees the locations of access data, and these locations can depend on the data content itself. So the adversary can infer sensitive information using the accessed locations. To defend against such an adversary, Goldreich and Ostrovsky proposed and formalized the problem of oblivious RAM. Of course, at their time, the cloud storage was not as popular as today, so they used the terminologies of random access machine, where we have a processor, it's like the client, and a memory like the server. The processor and the memory communicates using rewrite and the address of memory word in the memory array. Similar to the client-server example, all the memory contents are encrypted, so an adversary corrupting the memory can only see the accessed addresses of memory word, or it is also called the access pattern. To separate the problem of access pattern and encryption, we assume the adversary sees only the access pattern but nothing else. So this is the cleaner model of computation and the adversarial model. To formalize the security, we add in an extra layer of abstraction called oblivious RAM. The input to ORAM is a sequence of logical accesses, and the ORAM translates logical accesses into physical accesses. The physical accesses are observable by the adversary. To ensure security, we require the ORAM that for any sequence of logical operation, it translates into the same identical distribution of physical accesses. If we can do so, then of course the adversary can learn no information about the input data, the logical operations. This is a very strong notion of security. We call it a perfect oblivious RAM. There are two weaker forms of security called computational or statistical. There we consider a computationally bounded adversary, or the physical access patterns are only statistically close but not identical. The weaker notions of security are easier to achieve. For example, the computational setting, we achieve the logarithmic in n overhead, where the overhead means the ratio between number of logical accesses and the number of physical accesses. And n denotes the problem size, the number of memory words the ORAM simulates. So perfect security is very strong. It defends against an unbounded adversary. It composes cleanly in other protocols, but it also suffers a larger overhead. So our first question here is whether we can improve the efficiency of perfect ORAM. We have a second question, looking closer into the previous constructions of perfect ORAM. The running time is only in expectation. That means the algorithm is randomized. So the running time and thus the overhead of this algorithm are random variables. With good probability, the algorithm finishes in the claimed time bound, but with a small probability, these algorithms may run longer. I want to stress that in these running longer events, the algorithm remains perfectly secure and perfectly correct, because these constructions carefully ensure that for any sequence of logical operation, this small probability event happens identically. Still, the expected running time is less preferable because then other protocol using such perfect ORAM inherits the expected running time. So Raskin and Sinkin constructed the first perfect ORAM with a deterministic time bound to address this issue. The algorithm is still randomized, but the algorithm always finished in the claimed time bound with probability 1. So our second question is whether we can get the best of both results, that's a smaller overhead and a deterministic time bound. In this work, we answer both questions positively. We constructed a perfect ORAM that takes slightly less than qubit log overhead, and the time bound is deterministic. So we improved the deterministic time of perfect ORAM from square root to polylogarithmic in problem size. Also, this is the first improvement in running time since the first construction of perfect ORAM proposed by Damgaard, Meldgaard, and Nelson almost a decade ago. Before diving into our construction, it is a useful warm-up to see why earlier constructions of perfect ORAM has to run in expected time. The idea is follows. To securely access an array of elements in the memory, we cannot access them directly. That is not secure. So instead, we permute the array of elements uniformly at random. Then accessing an element in the permuted array reveals no information about the accessed element. But we have to do this random permutation under the adversarial eyes. A standard way to do so is to symbol random keys for all elements. Then we sort these elements using a sorting network with respect to these keys. So the keys and the elements are randomly permuted. In the case that these random keys collide with each other, we need to resample the random keys. And in this collision event, this random permutation can run longer. Fortunately, in the recent work on computationally secure ORAM, we developed a better random permutation that runs in deterministic time bound. So just by replacing the random permutation with the deterministic variant, we can obtain a deterministic time-bound perfect ORAM. But still, we want to improve the efficiency of ORAM. So we look into the construction of a previous work as well as our construction. We are all based on this hierarchical framework. The framework goes as follows. There are log n levels. The smallest level is only constant in capacity, and then the capacity grows geometrically until the capacity grows to problem size n. Each element is stored in exactly one level, and each level is uniformly shuffled. And there are some empty locations having no element. To access a desired element, the framework goes with two phases. The first phase is called fetch. We assume we already know the location of our desired element, but we touch one location per level to reach the desired element, and then we move the desired element to the top level of this hierarchy. Then this top level has only constant capacity, so it becomes full immediately, and then we have to periodically perform a second phase that's called maintain. The purpose is to reshuffle, repermute the elements in smaller levels down to a larger level. There are many missing details in this picture, but I want to stress that in the fetch phase, we need to first know the location of the desired element, but remembering the location of all elements takes a lot of space. So the idea in the previous work in Chang et al. Is to apply a recursive position map. The technique goes as follows. We group every two elements into one block. Then we permute the blocks in the hierarchy as previous. Now we just need to remember the half number of locations of these blocks. Because the problem size, the number of locations is reduced by a factor of 2, we can store them recursively in another perfect ORAM. So this is a recursive ORAM that stores the position in a larger hierarchy. The recursion stops in log n depth because the problem is reduced by a constant factor every time. And putting together the number of levels and the cost of performing oblivious random permutation, the total overhead becomes qubit log, as I stated earlier. To improve the efficiency, an essential observation is the following. We see that the fetch phase is much faster than the maintain phase. In the fetch phase, we just touch one block per level, so it's dominated by the cost of maintain phase. So our goal is to reduce the maintain phase time at the cost of slightly increasing the fetch phase time. To do so, we are inspired by the earlier work of Kushilevitz et al. We increase the block size. We group chi elements into one fat block. We will decide the parameter chi later in this talk. The point is, we say greater parameter chi, the recursive position map is reduced by a larger factor. So the number of recursion depth is smaller. It is now log n base chi or log n divided by chi. We hope this will reduce the cost of maintenance, but it is still not there. There are two major steps in the maintain phase, and we have a challenge for both major steps. We need to make the two major steps faster. The first step is to permute the 2 to the I fat blocks. Previously, our blocks are small, so it is faster, but now it's chi times larger, so the cost is chi times. In the second major step, after we permuted 2 to the high fat blocks, we need to update the corresponding pointers in the recursive position map, because the pointers in the recursive position map points to the permuted fat blocks. Now the positions are changed. To update these pointers, we found that these pointers are stored in fat blocks as well, so the cost of updating the pointers is now chi times greater. To resolve the first challenge, the idea is easier. It comes from the recent work on computationally secure ORAM. The main observation there is the following. We don't need to permute 2 to the I blocks from scratch. These fat blocks comes in separate lists, and these separate lists are already randomly shuffled inside each list. So all we need to do is to merge two lists into one single shuffled list, or it is called intersperse, two separate lists into one list. This intersperse is more efficient than permuting all the blocks from scratch. It takes only linear time, so we shaved a log m factor, that's the I in the cost. Challenge number 2 is more involved. We want to update the pointers for all the blocks that was shuffled in the previous step. We rely on two key observations. In the first observation, we see that there are only 2 to the I blocks that is shuffled. So there are only 2 to the I pointers needs update. The second observation is that just looking at the pointer, the value of this pointer, we can immediately decide whether this pointer needs an update or not. Why? Because we only shuffle blocks in level I. So if a pointer points to a block that is in a lower level than I, then this lower level block is not yet shuffled, so this corresponding pointer doesn't need an update. Using the second observation, we can immediately identify all the pointers that need an update, and then we can update these pointers in 3 simple steps. In the first step, we collect all the pointers into a short list, that's 2 to the I pointers. Then we obtain route and update these pointers from the shuffled blocks. Then we can put these updated pointers back to their originating fat blocks. These three steps takes time 2 to the I times chi for collecting the pointers into shortlist, and also 2 to the I times I for routing and updating the positions to the shortlist. Putting together, the total cost of the maintain phase amortized per element is proportional to chi plus log n. So we choose the parameter chi equals to log n, so it is absorbed by this additive term log n. Now we put back the fetch phase. We have a vector block, so it takes extra log vector to touch each block, and putting together two phases, the overhead is the lambda 1 less than qb log in n, and this is a deterministic time bound. So far, I have talked only about the standard sequential version of random access machine, and PRAM or parallel RAM is a standard or natural extension of RAM, and Oblivious PRAM is the natural extension of Oblivious RAM. It takes in as input a concurrent sequence of logical accesses, and then it accesses the physical memory using physical access pattern concurrently. We still require the physical access pattern be identically distributed for all logical sequences. We extended our construction from ORAM to OPRAM. There, the deterministic time bound is slightly worse than the expected variant. For the sake of time, I don't have time to go into the details, but it is because we don't have a very efficient parallel random permutation. There are still many open problems. For example, the gap between upper bound and the lower bound is still large. But after the result of this work, I guess it is more likely we have still have room to improve the upper bound side. Thank you for your attention. If you find this result interesting, I am happy to receive email, and please read our paper for details.